Hello and welcome to Mathematics with Simon. I'm Simon. We recently made a video on the remainder theorem in the A-level mathematics syllabus, and my friend Simon Howard asked a question about the proof of the remainder theorem and whether you could use the concept of degrees of freedom to prove the remainder theorem. And so we're exploring that in this video. There was a previous version of this video, but Andy Robertshaw found a mistake in it, so it had to be deleted. We can't have things wrong, so thank you to Andy for his feedback and to Simon for the original question. So what is the remainder theorem? I mean, just to recap, given a polynomial p of x, if we divide p of x by x minus a, then the remainder is equal to p of a. That is the remainder theorem. And the way we proved it was to say that every polynomial p of x can be written as q of x times x minus a plus r, the remainder. And every polynomial can be written in that form, where p of x is of degree n, q of x is of degree n minus 1, and r is a constant. And the point then is, if you substitute in x as a, the term q of x times x minus a disappears to 0, so you get p of a equals r. P of a is the remainder. So that's kind of how the proof happens. But the question is, well, how do we know that every p of x can be written in this form as given on the right hand side? And Simon's idea was, well, if p is a polynomial of degree n, it has n plus 1 coefficients, so n plus 1 degrees of freedom. And then you've got n in q of x and you've got 1 in r, so you've got the same number of degrees of freedom. So you can configure the right hand side always to fit the left. And broadly speaking, that works. I mean, I think that's a really good guiding principle. I think probably it looks to me, though, that it's a necessary condition, but not a sufficient condition to prove the remainder theorem. And we're just going to explore another example to see why that might be. So let's go back to simultaneous equations. So in simultaneous equations, we've got two unknowns, x and y, then two constraints, the two equations, and so those two constraints allow us to define the two unknowns. For instance, in this example, 4x plus 3y equals 10, 2x minus y equals 0. We're going to double the bottom one, which will tell us that 4x minus 2y equals 0. We're going to subtract them, which tells us that 5y equals 10. We're going to divide by 5, y equals 2. Y equals 2, which means 4x plus 6 equals 10, which means x equals 1. And if we substitute them back in, we can check that that's working. So x equals 1 and y equals 2. But it can be tricky. For instance, in this example, 4x plus 6y equals 10, 2x plus 3y equals 5. Well, if we double the bottom one, it's just the same as the top one, which means we've only really got one equation, which means there's an infinity of possible solutions. I mean, you could say, well, that's not really two constraints, it's just one constraint. But here's another problem. 4x plus 6y equals 10 and 2x plus 3y is anything that's not 5. I mean, so let's just say it's 0. So if you double the bottom one, then you get 4x plus 6y equals 0, which contradicts the top one, which means there's no x's and y's that can satisfy both of those equations, so there's no solution. And basically, geometrically, this is just two parallel lines that just never meet. So there's never a point when the lines cross, which would be the solution. Whereas for this one, there's just the same line. They're just two versions of the same line, so they're meeting everywhere. So there's lots of pairs. Every pair of x's and y's on the line satisfies both equations. So what we're really saying is degrees of freedom is indicative and it's helpful, but it's on its own probably not quite enough. So another way would just be to literally grind it out. So we're just trying to find new proofs now. So let's say we're going to divide ax squared plus bx plus c by x minus r, for example. So if we just grind out the polynomial division, and actually we've got a video on polynomial division as well, so it's x is into ax squared gives us ax, then ax times x is ax squared, ax times minus r is minus arx. We take that off, so we end up with b plus arx, and we bring down the c. And then how many x's in b plus arx? Well, there's b plus ar. So then we do b plus arx is there, and then b plus ar times minus r we have on the right. And then if we take this bottom row away from the top row, what we have is AR squared, which is there. Then we have minus BR, which is plus BR. And then we have a C from the top. So it's AR squared plus BR plus C. So that's exactly right. So the remainder that we have got is just the polynomial when we substitute it in R. By the way, using R here is slightly confusing. R here does not signify the remainder. R is playing the role that A did up here. It's just that we couldn't use A because we got AX squared plus BX plus C. So we used R instead, but we mustn't get confused and think that's the remainder. Anyway, so the point is the remainder when we divide AX squared plus BX plus C by X minus R is AR squared plus BR plus C, which is what we were looking for. So we've proved it constructively by polynomial division for quadratics, but not for all polynomials yet. So another proof is by induction on the degree of the polynomial. So for those that are not familiar with the induction process, so in proof by induction is in the further maths syllabus. This is an A-level maths video, but it's probably pushing the limits of A-level maths. This particular concept is further maths. But when we were at school, we were taught to read around the subject. And I think more broadly as well, go where your curiosity takes you, or the curiosity of the people you're studying with, and actually having, good people around you who ask good questions and push you is very important to your mathematical growth, probably as important as your teachers. And I'm lucky enough to have been studying with Simon since we were 17. Quite a while. So, yeah, I think that's an important thing to think about is, ideas that you get from your other students are always really helpful. So, proof by induction. So the first thing is, so we start by assuming the theorem is true for polynomials of degree n minus 1. We then use this to prove that the theorem is true for polynomials of degree n. So prove it's true for polynomials the next degree up. And then if we can prove it's true for polynomials of degree 1, then it must be true for degree 2 by using those two rules above. And then if it's true for 2, it must be true for 3. And if it's true for 3, it must be true for 4. And all the way up, so it must be true for all positive integers, all natural numbers. So it's a very clever method of proof, and it's used in lots of contexts. It's used for sequences and series, but it's used all over the place in more advanced mathematics. So we're going to use it here. So the point is, so let's write, so let Px be of degree n, and let's assume that for all polynomials of degree n minus 1, you can write them in this form, the form we talked about, which is x minus h times a quotient plus the remainder. So what we're going to do is now we're going to look at polynomials of degree n. So we're going to say Px equals axn, then plus t of x. So t of x has a lower degree. So now we know we can write tx in the desired form, and now we're going to rewrite ax to the n. And we're going to rewrite it in this slightly strange way. We're going to write it as ax to the n minus 1h plus a times x minus h, x to the n minus 1. Now you might think, why on earth are we doing that? But we're doing it for a really good reason. So firstly, let's just make sure this is actually ax to the n. So what you've got is you've got a times x to the n minus 1, which is the ax to the n bit. Then you've got a times minus h times x to the n minus 1. Then you've got a times h times x to the n minus 1. So these two terms cancel. So this is indeed just ax to the n. And the point about this is a polynomial of lower degree, of degree n minus 1. This is just x minus h times a polynomial, and this is t of x. So what we've got here is we know that t of x plus ax to the n minus 1h can be written in the form qx times x minus h plus the remainder, and then we know the middle bit is just x minus h times a polynomial. So we've now got p of x into the desired form. So now what we could do is set x equal to h, and then all this stuff would cancel out, these two, and you just get left p of h equals r, the remainder, which proves the theorem. So we assumed the theorem for degree n minus 1, we've proved it for degree n, and now we're going to prove it for degree 1. P of x equals ax plus b. This is the polynomial of degree 1. We're going to write this in a different way. A times x minus h plus b plus ah. And again, what we've got here is a constant on the right, b plus ah, and then on the left we've just got x minus h times a polynomial that happens to be a constant a. So again, if we were to put h in here, we get p of h equals the remainder here, b plus ah, which is what we're looking for. So we've proved it for degree 1, and then we've shown that if we assume it for degree n minus 1, it's true for degree n. So it's true for all integers by induction. So just going back to this idea of the grind, so I'm trying to prove this in numerous ways. We did this grind thing for quadratics. We want to do it for polynomials of all orders. So here's a thought. What's the remainder when 54 is divided by 10? Well, it's the same as the remainder. This should say remainder, not remain dead. The remainder when 44 is divided by 10, or when 34 is divided by 10. The point is, taking 10 off doesn't change the remainder, because in a way, division is just iterated subtraction. And in the same way, what's the remainder when px is divided by x minus h? Well, it's the same as the remainder when px minus x minus h is divided by x minus h. So if we take x minus h, or a number of them, off px, we don't change the remainder. We don't change the remainder when we divide by x minus h. So we can take a bunch of x minus h's off and not change the remainder. Okay, so let's just imagine p of x was ax to the n. This is the kind of grind approach. Again, we're going to write that as x to the n minus 1 plus ax to the n minus 1 times x minus h. We can now see that's the same thing as the top row by just expanding the brackets. And then we're going to do another move. We're going to write that as ah squared x to the n minus 2 plus ax to the n minus 1 x minus h plus x to the n minus 2 x minus h. Now, again, if we expand out these two brackets, we can see that this whole expression is just ax to the n. But the point about this is that this polynomial ah squared to the x minus 2 must have the same remainder when it's divided by x minus h as the original polynomial did, because all we've done is added on a bunch of x minus h's, which shouldn't make any difference to the remainder when we divide by x minus h. And the point about that is, if we keep going with this process that we're looking at, we can change ax to the n to ah to the n plus some great big polynomial t of x times x minus h. Because all we do is, again, we're going to add on, the next thing we're going to add on is ah squared x to the n minus 3 times x minus h, and kind of so on. And this front term, each time we do this, the front term will swap an x for an h. So it will slowly move over to ah to the n. And so the point is, given ax to the n, bx to the n minus 1 plus dot 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 plus k, we can carry out this kind of transformation and change the whole thing into ah to the n plus bh to the n minus 1 plus dot dot plus k, which is just a constant. It's just a constant. So this is then the remainder if we divide the original polynomial by x minus h. Okay, so this is like a direct proof of the grind, and actually some people will realize that actually all we're doing is polynomial division in another way. It's actually just another way of expressing the polynomial division algorithm. And actually also we could prove this in a slightly more tidy way by induction. So we could say, let's assume the remainder theorem is true for polynomials of of degree n minus 1. And then what we're going to do is we're going to write this polynomial of degree n by ax to the n plus bx to the n minus 1 plus dot 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 plus k. And then we're going to rewrite this front term again, same trick, as a h x to the n minus 1 plus a times x minus h x to the n minus 1. And then what we've got here is, if we think of the remainder when we divide by x minus h, the first term is just a polynomial of degree n minus 1. So we assume that by the induction hypothesis, the remainder is just a h h to the n minus 1. The middle term, again, is a polynomial of degree n minus 1. So we can assume the same thing, and this one's going to go to 0. And then the same is true of the later terms. They're all polynomials of degree n minus 1. So we can put in h for all of the x's, and we basically get remainder polynomial of h equals a h to the n plus b h to the n minus 1 plus dot 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 plus k. I suppose for absolute completeness, we have to also prove it for the case when the degree is 1. But the good news is we did that up here. So here we proved it, the bottom line proves it in the case when it's just a direct calculation, when the degree is 1. So that's the kind of foundation for the induction step. So actually here we have proved the grind, or actually what I would call a constructive proof by induction. Because the point is, this other proof here, which is still a correct proof, this proof isn't strictly constructive. It shows you the result is true, but it doesn't actually calculate the formula. In a way, it's kind of beautiful because it's so simple. But what's nice about this approach, and then later this, or this, is you're actually calculating the formula and showing how it comes about. And that's quite satisfying because it shows you how it's constructed. That's kind of why it's called a constructive proof. I hope you like this video. If you do, please hit the like button. You're very welcome to subscribe and hit the notification bell. I think this one has been a bit harder than the normal videos because I've been pushed by people asking questions. If that's the case, I would encourage you to just go with it. Even if you understand half of it, the other half might go into your subconscious mind, and later on it might all fall into place. So it's often good to try for things even if they feel a bit challenging. I'd love to hear all of your ideas, and most of all, I hope you enjoy your mathematics.